So good morning, everyone, and welcome to SpaceGeekSpeak. Today, we're honored to have Dr. Bonnie Buratti with us. Dr. Bonnie Buratti is a senior research scientist at NASA Jet Propulsion Laboratory, JPL, and a leading expert in planetary science, particularly in the study of icy worlds and outer solar system bodies. Her research focuses on understanding the surfaces, compositions, and physical properties of moons, asteroids, and other planetary bodies through spacecraft observations and remote sensing. She has contributed to numerous NASA planetary missions and plays an important role in advancing our understanding of ocean worlds, environments that may hold the conditions necessary for life beyond Earth. Today, she will be discussing and presenting to us NASA's Europe Clipper mission and its journey to one of the most compelling destinations in our solar system, Europa, a moon that likely harbors a vast ocean beneath its icy shell. Please join me in welcoming Dr. Bonnie Buratti. Thank you.
Thank you so much, Svetlana. Okay, I'm going to talk about NASA's major mission to the outer solar system. Actually, right now, it's the only flagship mission to the outer solar system, Europa Clipper. I don't think there's any question more important than are we alone? It's really one of the great questions that we're facing now. And associated with that is the question of how does life arise? When I was in graduate school decades ago, the view on how life arose on the Earth was followed the Urey Miller experiment. This is Stanley Miller in his lab at the University of Chicago, and his experiment replicated the atmosphere of the ancient Earth, or at least what they thought it was back then, with methane, ammonia, water vapor, hydrogen, and he replicated this atmosphere and zapped it with electricity. And lo and behold, amino acids form. And somehow life arose from these amino acids in shallow seas. So I got my PhD from Cornell, and Carl Sagan was one of my students. I was one of his students. And in his lab, Bishan Kari, this is a picture on the right of Bishan Kari, Ed Saltpeter's on the left. He's another illustrious astronomer, Carl Sagan and Bishan Kari. They've all passed away, but this is the lab in Carl Sagan's lab showing Kari extending these experiments of Urey and Miller. This shows him, he was somewhat often called a cooker with his experiments creating what Carl Sagan called intractable polymers or tholins. These were materials that were rich in organics and amino acids. So this is kind of the view back then of where life on Earth arose. This is an early Earth, and you can see these mats at the bottom. They were called stromatolites, bacterial mats. This is how we thought life arose back then. But now we think that life arose in these thermal vents in the Earth's ocean. Here's a view of some. And the reason that we think that is if you look at some of the bacterial forms that exist at these ocean vents. I mean, it's teeming with life. Here you see, crabs and look like lobsters or shrimp. But also there are primitive bacteria in these oceanic vents. And it turns out that those bacteria are at the trunk of the tree of life. Here is a rendition, a simplified version of the different types of life on Earth. And if you look at the base here of that tree, you see the last universal common ancestor who lived in this high temperature water of deep sea vents near the ocean floor, magma flows. Okay, so that's how we think life arose in these deep oceanic thermal vents. So NASA's search for habitable environments has been to search for liquid water, which is necessary for life as we know it. I'll only be discussing life as we know it. It turns out that on Earth, everywhere you have water, you have life. So, so far up until now, we've really searched for habitable environments on Mars. And I'm only going to talk about the search for habitable environments. Actually finding life is kind of ambitious. So the Europa Clipper mission is only searching for habitable environments. So here is the first picture we obtained from Mars. This is a Mariner 4 picture. And, I was brought up on tales of life on Mars and, um, even uh, people like Lowell, Percival Lowell, thought that there was intelligent life on Mars. And when you saw the central portion of Mars, the equatorial regions, getting darker in the Martian spring, he thought that that was water being brought from the polar caps to lower elevations to for farming. And there were various labs on Earth where scientists were growing plants in Martian environments. So when this first picture of Mars came back, and I remember, this was, I can, remember this. I was in I believe, elementary school, and these were the days when great space missions were broadcast on television to the whole nation. So this was really disappointing to see this cratered world where life really could not exist. It looked more like the moon than the Earth. But then some of the later missions that orbited Mars, the Viking orbiters, showed that Mars really did have some features that suggested that water was on its surface. Here's an image from one of the orbiters showing a lot of geologic features suggesting running water. And there are, in fact, uh, the polar regions of Mars actually show evidence of shorelines in the past. So we believe that Mars was really covered with water, including oceans. And the evidence for that, here's Perseverance, the Mars 2020 rover with a little helicopter, Ingenuity, and you can see that there are, in fact, sedimentary rocks on the surface of Mars. Here's a close-up showing that not only was there water, but there was standing water where life could have arisen. And we believe that Mars looked more like this in the past, with an ocean, oops, with an ocean at the northern pole. Okay, and possibly greenery and plants. Okay, this is Pathfinder, that one of the earlier rovers. It just shows how much like Earth. This is Death Valley. That's Mars, and this is Death Valley. In fact, this is a test. JPL likes to test a lot of its equipment out at Death Valley because it's so much like the surface of Mars. There it is. Okay, let's get on to the main subject of this talk, which is Europa. Um, Europa is one of the four major moons of Jupiter discovered by Galileo. This is Io Europa, Ganymede and Callisto. And if you're not familiar with Europa, I'll give just a little bit of background. First of all, it was discovered by Galileo, the man, not the spacecraft, in 1610. Here's a picture from his notebook, Sidereus Nuncius, that shows the moons orbiting Jupiter. And as you probably know, this led to the demise of the geocentric view of the solar system in which the planets orbited around the Earth and the sun as well. But this suggested that smaller objects orbit around their primaries, just as these moons orbit around Jupiter. So the Earth and the planets orbited around the sun. It's also important to realize that Galileo was not the first person, or Copernicus was not the first person that supported the heliocentric view of the solar system. The early Greeks, people like Eratosthenes, who measured the size of the Earth, they also had a heliocentric view of the universe, but it kind of fell out of disfavor with the Pythagorean and the Ptolemaic view of the solar system, of the universe, which they thought They thought that was the universe back then. Okay, some facts about Europa. Um, it's about 5 times the distant from the sun, which means it only gets a few percent, about 4% of the sunlight. That's important. It orbits the sun about every 12 years, orbits around Jupiter about every 3.5 hours. It's a little bit smaller than the moon, and it's very reflective. It's very bright. That's an important fact to remember too. It only has a trace of an atmosphere, and the composition is mainly ice and rock. These are all important facts about Europa. So here's another thing about Europa. I think this is key to this talk. When the Galileo spacecraft went there, you probably all know that Europa or Jupiter has a very strong magnetic field, many times, thousands of times stronger than the Earth. But of course, we knew that when Galileo went to Jupiter. But it discovered that Europa also has an induced magnetic field. Now, if you remember from, well, you all took physics and physics in college. If you have a magnetic field um, moving across a conductor, it's going to induce a magnetic field within that conductor. This is Faraday's law, Faraday induction. And if you what the Galileo spacecraft discovered was that Europa also has a magnetic field, which implies a conductor. And the only logical thing that it could be would be liquid water. So this was how the first hint that there was a massive liquid ocean of water underneath this ice shell on Europa. And we know it's ice from spectroscopic measurements from Earth. We knew that before Galileo, and it's very bright. Now, if you live in the Northeast, um, you know that the that snow gets dark very fast. Okay, so from cinders and stuff. So if you have bright ice, that kind of implies a active geologic process. Okay, so this is our view of what we think Europa's interior looks like. There's this ice crust. Okay, and we'll get to some of those fascinating features. There's a subsurface ocean. There's a rocky mantle, and there may be a metallic core. That hasn't been proven yet, but models suggest that there's a magnetic core, a metallic core, also magnetic. Okay. Now, there's another important fact here, and that is Europa gets heated by Jupiter due to the tides. Europa is orbiting Jupiter, but the orbit is not completely circular. It's slightly oblate, so that elliptical, so that the distance changes. So the tidal force is higher when it's close to Jupiter and less when it's further away. So Jupiter kind of flexes. There's a mechanical motion of it flexing back and forth, and that energy, that mechanical energy, is dissipated as heat energy. So it gets heated, and that causes the mantle we believe to have a heat source. Well, we know it has a heat source. I'll come back to that later. Okay, actually, it's in this figure here that because of that heating, it may have thermal vents at the top of the mantle, the base of the ocean, the liquid ocean, similar to those thermal vents on Earth. Okay, so you see this heating causing thermal vents like those on the Earth. And that may even cause plumes on the surface, and it may also cause active geology on the surface. We'll get to the active geology, but the question arises, are the ingredients for life there on Europa? Is there a habitable environment? So the essential elements for life are liquid water, some type of food, organic molecules that life could use to grow and reproduce, and some type of energy. As I said, the sun is only about 4% of what it is on the Earth, but the chemical energy, well, the energy might be provided by these thermal vents, but also their reactions, these so-called redox reactions, where electrons are being exchanged between molecules, and that causes an electrical charge to be set up. So that could actually cause this, uh, provide the energy that organisms would need. And also important is stability. We believe that this situation has been there for billions of years. The solar system is about 4.6 billion years old, and a large fraction of that, this situation could have existed. Okay, so this is actually an official NASA image from, I don't know, a couple decades ago when people first started thinking about exploring the ocean of Europa to look for a habitable environment. You can see these vents here, sometimes called smokers, and there's a probe. Now, we think the ice crust is about 20 kilometers thick. The ocean itself is about 80 kilometers. This is one of the things that we're trying to find out. But I mean, we don't really have the technology to get through that ice crust now. I mean, even on Earth, it's only recently that we've been able to explore the lakes underneath the ice shelf in Antarctica. But anyway, it's fun to dream about these missions. Okay, so if we look at the surface of Europa, it is filled with these intriguing features. There are you see these blobs here called lenticuli, which look like there's something almost bubbling up from the surface. But even more interesting are all these cracks that look like the ice shell broke from some active geologic process. And you can see that they're episodes. You can see that there are overlying features, like this crack overlays these cracks here. This blob here, this lenticula, overlays the crack, which are called lineae. Okay. Looks like there was some kind of a crustal movement here. It's like it's a very geologically active world. And what's also important is there are compositional changes. One of the goals of the mission is to look for organics on the surface. So here we have this dark red material. And when Stanley Miller and Bishankari did their experiments in their labs with a primitive earth, this tholin material, this material that's rich in organic molecules and amino acids that they created, was reddish in color. So we think that there might be some kind of organics in this red material that we're going to look for. And if you look at these cracks here, um, you can see that it almost looks like there's some kind of material coming out from the surface and being deposited on the edges of these cracks. It's really a fascinating world. Okay, so here are the instruments we're going to use to explore Europa and the goals that are associated with each of these instruments. Now, as I said before, Europa Clipper is a flagship mission. It's a big mission. It's a $5 billion mission to the outer solar system. The only one right now headed towards the outer solar. Well, actually, there is another mission there, but it's not a flagship mission. Juno is a New Frontiers class mission, a smaller mission. It's out there already studying. And the European Space Agency also has a mission, JUICE, that's on its way. But I'm only going to be talking about Europa Clipper. Okay, so it has the usual instruments that a flagship mission has. It has a camera, two cameras actually, a narrow and a wide angle camera for studying the geology. And then is a slew of spectrometers. There's a ultraviolet spectrometer to look at the surface and the atmospheric composition, and if there are any possible active plumes on the surface, like this one we see here, what is the composition? There's a thermal imager searching for hot spots, active geology. There's an IR spectrometer that is going to look for the chemical fingerprints, the spectra of things that are on the surface, or especially organics and evaporate deposits, things that are uh, evidence of liquid water that came and went, that sublimated. And then finally, there's a very innovative ice penetrating radar and I'll talk about that more later, that will study the characteristic of the ocean and also the ice crust, how thick it is. There are various fields and particles instruments. There's a mass spectrometer to understand the composition of this very thin atmosphere in the plumes. There's a dust analyzer to look at the particles in the region. There, of course, there's a magnetometer because from the magnetic field we can tell about the interior and the nature of the ice of the ocean underneath the ice crust. There's a plasma detector to study the charged particles in the environment. And finally, the antennas on the spacecraft are going to be used to understand the shape of um, of the moon by how it tugs on the spacecraft. Okay. All right. So here is a nutshell of what the scientific goals and the objectives of the mission are. Um, the overall goal is to explore Europa to investigate its habitability, whether life can exist there. As I said before, it's not a life detection mission. It's just too ambitious. If there is life, it exists way below the surface, and we don't have the means to detect it. But we're just looking at whether life could thrive there. So here are the main scientific objectives: to characterize the ice shell and any subsurface water, including how mixed up it is, study the ocean properties, especially how salty it is. Because as I said before, it's those materials like salt that may provide the energy through these redox reactions of exchanging electrons. And also we're looking for the nature of the surface and the ice ocean exchange because we can observe the surface. We're trying to understand the composition of Europa's ocean by studying the surface, what's left on the surface from possible plumes, and finally to understand the geology, understand the formation of surface features, including sites of recent or current activity, and characterizing interest localities that we've identified from previous missions and also possibly ones that we might discover then. If we find a plume, we'll really focus on studying it. Okay, so I think I mentioned briefly that there is some evidence that there are plumes on Europa currently happening. Here's at the lower, that bluish image there on the lower part of this slide shows a Hubble Space Telescope image of possible OH molecules. And also the Galileo spacecraft observed what is probably a plume, not with the camera, but the magnetic field seems to be draped over a feature on the surface, which is likely a plume. Okay, so that's the mission in a nutshell. Here are the instruments being installed on the vault in the clean room at JPL. There's a couple instruments. The cameras are down here. SUDA, that's the dust detector, and mass specs is the mass spectrometer. Now, this is the biggest spacecraft we've ever flown. Um, there is the Space Launch System. There's a Statue of Liberty. Um, 6 stacked school buses. This is the SpaceX Falcon Heavy. This was the rocket that launched the mission. There's Europa Clipper. So there's a basketball court. It's about as big as a basketball court. It's weighs a couple tons. It's really huge. The biggest part, of course, is those solar panels. The solar panels are they're not the largest solar panels in space. The space station has bigger panels, but in deep space, it is the largest set of solar panels that have ever been flown. And they're more efficient than the solar panels, that you put on your roof. They're typically home panels are typically in the low 20%, whereas this is nearly 30% efficient. So this is an example of space serving humanity. A lot of the technology that we've developed for space is seen in the civilian sector. So these more efficient solar panels will soon be on people's rooftops and solar farms and stuff like that. So innovation at work. Okay, so I did want to talk a little bit about the reason antenna. They it doesn't show it here. By the way, Airbus in Holland did produce this, did build the solar panels. Um, actually, I think that image comes later where I show the reason antenna actually, it's not like we're not using the main bowl-shaped antenna for radar. There are these dipoles that are attached to this to the side of the solar panels that are going to be used to provide information similar to what similar instruments have provided on at Antarctica. Okay, so here we see the ice shell, um, and this is floating ice, and this is where we see the grounded ice. You can see the liquid water and some of the subsurface features here in Antarctica. Okay, and we actually tested this device, this newfangled radar mapper, when we went by Mars on March 1st, 2025, last year. So here, this was near the equator, and we got images of some craters and stuff like that on Mars, kind of the older terrain. Okay. So here is Europa Clipper being encapsulated into the Falcon Heavy and transported to legendary Launch Complex 39. I was there at the launch. It's quite really interesting. I have the launch photo here. Let's see if I can get the sound up. There we go.
Europa Clipper, unveiling the mysteries of an enormous ocean lurking beneath the icy crust of Jupiter's moon, Europa.
Okay, so that was the obligatory launch video. Okay, here's the mission. So it was launched actually it was launched, that was when the launch window opened. It was actually launched on the 14th of October. And by the way, there was a little drama we had at the launch. We expected to have good weather, but a few days before the launch date, the opening of the launch window, this Category 5 hurricane, Milton, uh, came barreling out of the Gulf of Mexico. It was going towards Cape Canaveral, and the path put it right over Launch Complex 39. So we did have a hit of a hurricane. It actually hit our hotel. I was really scared. I mean, there were tornadoes. You could see tornadoes because these are these squall tornadoes that are at the front of a hurricane. A big tornado hit our hotel, caused some damage to the roof, and there are all these buildings around damage, and there were fatalities in this hurricane, not up where we were, but down a little bit south. But we couldn't launch on our open date. But the fabulous, fantastic Army Corps of Engineers came in and cleaned up the launch pad, and we launched only 4 days later after this Category 5 hurricane. I think it was down to a Category 3 or 4 by the time it hit us, but there was major damage at the launch pad. We had to put the spacecraft and the rocket back into the protective building that it came out of. So there was really a lot of drama with this launch. Okay, so we launched, and then only about 4 or 5 months after the launch, we had a Mars gravity assist. Now, this does not have a direct route um, to Jupiter. We have just like previous missions to the outer solar system, because we don't have a rocket that is powerful enough to launch it on a direct trajectory. We have to do this thing where we loop around the inner solar system and get gravity assists, momentum assists from planets in the inner solar system. Okay, so we went by Mars in March of 25 last year. Then we're looping around again to an Earth gravity assist in December of this year. And we are planning on taking some unique calibrations and tests during that period, end-to-end tests. And then we enter Jupiter orbit insertion is in April of 2030. So the time of flight, we have a long cruise of 5.5 years, but we are really busy, planning the software that we need to do the science observations and testing the instruments. We're really busy. Okay, let's see. Now this is the only eye chart I have in this talk, and it's not necessary that um, you know, look at this in detail, but it's just to drive across the point that this is rocket science. This is really, really complicated. Okay, so just to mention this important point, we are not actually orbiting Europa. Europa. We are orbiting Jupiter, and the reason for that is Europa is close to Jupiter, and the particle environment there, charged particle environment, the radiation environment is really, really dire. So we don't want to expose our instruments, the electronics on board the instruments, to anything that is to any more of this than we have to. So we actually spend most of our time. Remember Kepler's laws. You have second law that you have your velocity out here when you're further away from Jupiter is less. So you actually spend most of your time out here, far away from Jupiter, and we swoop in to fly by Europa 49 times in the mission. So here's just a typical orbit and all the things we do. We point the spacecraft, and I thought I did have an image of the instruments on the spacecraft where the imagers are pointing directly down to the surface of Europa, whereas the fields and particles instruments are in the RAM direction to scoop up particles and kind of study them. So this is the RAM. This is the period when we're observing this kind of brown mustard colored part of the orbit. And then this is a bulk data system. There's a filter where we classify the data as to how important it is to uh, send back to the Earth. So then we have a cleanup maneuver here, a calibration. Um, there's some kind of BDS maintenance here. We do a target maneuver. We filter the data on the BDS. Let's see, there's the approach maneuver, another calibration, an ephemeris update. Then we take some other data with SUDA out there, surveying data. There's another ephemeris. We uplink the ephemeris. PIMS does a roll. This is the charged particle, the plasma detector. So we roll the spacecraft to get the three-dimensional view. We do a ephemeris uplink again, and then connect with the deep space network here. And here's the approach, and there's closest approach for our observation. So this is a typical uh, encounter, a typical flyby. And this is why we're so busy. This is so complicated to try to get. I mean, just the bulk data system. I mean, it's unlike anything we've ever flown before. When the mission I was on before this one was Cassini, and the data storage on the spacecraft was only about 4 GB, but this is like 100 times more. So this is really a lot of new technology. And here are the operations. The ground tracks from these 49 flybys will in fact capture almost the entire surface, even including the polar regions, which are difficult to get to. It has some of the interesting geologic features here. Puil is the only really major crater. Thrace is where it looks like a whole slurry of materials came out onto the surface. Okay, so here is kind of looking ahead. This is the first, Europa Clipper is the first detailed observation of a ocean world, but we believe that these ocean worlds are common in our solar system, and in fact, probably in other solar systems. I mean, probably are aware that there have been something like 5,000 exoplanets discovered in our galaxy, and some of these are probably ocean worlds. So Europa is the first world, but Ganymede probably has a subsurface ocean, possibly Callisto. Io doesn't, because all the water is just, as you know, there are a ton, dozens of volcanoes on Io, the first Galilean moon, and sulfur volcanoes, and all the water has been outgassed. But Enceladus, we know, has a subsurface ocean. Here's a little picture of a plume from Enceladus. This is from the Cassini mission. Triton, the giant moon of Neptune. Titan has at least a partial ocean moon, is an ocean underneath it, possibly Pluto. And of course, there's Earth here, has a surface ocean. So this is the first time we are just really investigating an ocean world in detail, looking for a habitable environment. So I want to leave plenty of time for questions, but I did want to talk and with this tradition among NASA where we always send something of ourselves into the outer reaches of beyond the solar system. So this the first really notable one was the Voyager record, where 116 images from Earth were put onto this record. And on the surface of this golden record, there is some basic information about the Earth. This is like a little technology thing about how to play the record. There is the position of the Earth with respect to some pulsars in our galaxy. They're fairly long-lived, so if this record is picked up a billion years from now, and actually there was a Star Trek episode. If you're a Trekkie, there was a Star Trek episode about the capture of this record of the Voyager spacecraft from alien. I forget which alien life it was, but yeah, that shows our position. And here's just various things about the water molecule, the source of life. And here are some of the 116 images that were included in this record, typical things on Earth. Now, I was at Cornell when this record was being put together. Carl Sagan led this. In fact, he had a book written on this called Murmurs of Earth. And some of these people here I actually knew. In fact, here, the lower right here, second from the bottom, this is Val Boryakov. This is George Hay-Lew and Wendy Gratis. And I knew all these people. And I know that Val has passed away, but George Hay-Lew still works at Caltech. I actually see him occasionally. He was my office mate. So quite familiar with some of these pictures. Okay. So we have our own plaque on the spacecraft. Okay. This is the plaque. And what it is, on one side, we have the waveform for water in a little over 100 languages. This is the plaque that is on the outside of the spacecraft. And facing the inside is a plaque that shows the Drake equation. This is the equation that estimates the number of technological civilizations that might exist in the galaxy. And here is this message in a bottle. And there's actually a chip. It doesn't show the chip here, but it has a chip of about 2 million Earthlings who signed their names. And here is the waveform of the water molecule. And this is Ron Greeley, who was actually the project scientist is Bob Pappalardo. I'm the deputy project scientist on the mission. And I should have mentioned early on that this is a group effort. I'm just speaking for hundreds of people. I mean, when we were in assembly test and launch operations, we had 500 people just at JPL working on the mission, and then hundreds of people on the outside. So this is a whole team effort that I'm just speaking for thousands of people that have worked on this. I think it's altogether about 2,000 people have worked on this mission. So Ron Greeley was, he passed away before his time. He was the project scientist, Bob Pappalardo, his thesis advisor at Arizona State University. He really was one of the drivers, the early drivers of the conceptual stages of this mission. But here's, I think, really the best thing. Ada Limon, who was the poet laureate, the last poet laureate, wrote a poem just for us, okay, in praise of mystery. And I'm going to end this talk by actually reading the poem. I can't do it justice, but I am going to read the poem add some art here to the scientific discovery that NASA is so great at. So I think I have it up. It is online. You see here, I'm going to try to get back to my browser. Ignore all the cat videos and stuff. Okay, so here it is. This is the poem that Ada Limon wrote just for us. Okay, I'm going to end by reading it. In Praise of Mystery, a poem for Europa. Arching under the night sky, inky with black expansiveness, we point to the planets we know. We pin quick wishes on stars. From Earth, we read the sky as if it is an unerring book of the universe, expert and evident. Still, there are mysteries below our sky, the whale song, the songbird singing its call in the bough of a wind-shaken tree. We are creatures of constant awe, curious at beauty, at leaf and blossom, at grief and pleasure, sun and shadow. And it is not darkness that unites us, not the cold distance of space, but the offering of water. Each drop of rain, each rivulet, each pulse, each vein. O second moon, we too are made of water, of vast and beckoning seas. We too are made of wonders, of great and ordinary loves, of small invisible worlds, and in need to call out through the dark. Thank you. I can take questions now. Thank you.
Thank you so much. Wow, this all I can say is just absolutely wow. It's so fascinating, and I bet that you being at the launch, it was such a special meaning to you. I can only imagine that how fantastic it was felt for you and for a whole team that while you were watching that rocket lifting off with the results of the quite a long journey. I posted a link to the Library of Congress where that poem is cataloged and everyone can have access. And I believe that there's also a recording of that poem where Ada Limon reads it himself, themselves. So if for attendees, if they would like to get access, they're welcome to use that link. And now questions. I posted some questions, and in case if there's none from the audience, but I wanted to open the platform for audience if anyone would like to ask anything.
Well, I have a couple of comments. And my first comment was that the picture, one of the first pictures you showed came from, you said, a Viking orbiter around Mars, and it showed obvious erosion from some liquid, most likely water. And but that same picture, that same area was taken by the Mariner Mars 71 mission several years earlier, and a lot less resolution though. But from that picture, the scientists said that it looks like there's been some erosion from a liquid, some kind of liquid, and they wouldn't say water, but it was some liquid erosion. And there were a lot of other pictures taken by Mariner Mars 71 in 1971 that indicated a lot of liquid erosion. And so that was further confirmed by Viking years later. But
Yeah, we have a joke, among NASA scientists. I try to just get the best picture of that area
yeah,
to show my point, but we have a joke among NASA scientists that water has been discovered, surface water has been discovered on Mars dozens of times. Every mission we have to announce that discovery.
yeah,
Yeah, so yeah, thank you for that insight that there's been a
yeah,
lot of lot of evidence
Yeah.
that there is liquid water and standing water. That's the real important thing.
Yeah, yeah. But before that, like you said, Mariner, yeah, Mariner Mars uh, 4, I guess, discovered the craters on Mars, and up until then, we thought that there was water flowing from the poles into the equator areas, and
Yeah.
maybe some life that was
Yeah.
determining canals and so forth.
Yeah,
As a matter of
actually,
fact,
that was something that Percival Lowell espoused, but as it was pointed out by numerous scientists based on theoretical models of the expected temperature and pressure at the surface, that there couldn't be liquid water. Even at the time of Lowell, that whole theory was criticized. Although it did stay on in the public imagination that there was liquid water on the surface of Mars,
yes.
even up until, we discovered that it wasn't.
Yeah, and I remember in the 1950s, scientists were saying that, well, the people on Mars probably are very tall because there's less gravity on Mars and you can grow
Yeah.
very tall. And also, they have immense chests, they have big lungs, monster lungs, because they have to breathe in a lot to get the kind of air that
Mhm.
you need to have that life. So, there are a lot of determinations about what life must be like on Mars until uh, Mars 4 came along, Mariner 4 came along and showed all the craters, and it was depressing. It was a very depressing picture. A lot of interest was lost in Mars after that picture. One other comment is Carl Sagan had that very comprehensive plaque that showed a lot of things about the Earth, assuming someday the Viking mission will encounter some intelligence, and then they can understand where other life on our solar system. But before that, Carl Sagan made a plaque for the Pioneer missions, which were at that time envisioned to be the first spacecraft to leave the solar system. And that plaque, as you may know, it looked something like this, if you can see it. And so it showed, I guess the light is kind of reflective here, but it showed a very detailed picture of how to find the Earth in our solar system with pulsars, this pulsar chart. And I think they had something very similar on the Viking
Yeah.
plaque.
Yeah. Yeah, that
And
was on the plaque there. Yeah.
but it also showed a picture of what the kind of life is like on Earth, the kind of life that came with this kind of technology. And and a few other minor little things, but it was very minor compared to what Voyager had. And so, but that was the first plaque, I think, that was sent out of our solar system,
Yeah.
talking about where the Earth is and what life is like on the Earth. And so those are the only two comments I had. Otherwise, it's a great presentation and very good, and I appreciate the information that you gave. I was going to also ask, do you know a professor from SC named Karen Lloyd?
No.
Okay, I heard a talk by her a week ago, um, and she studies what they call intraterrestrials. Intraterrestrials are little microbes that live underneath the surface of the earth and underneath the ocean. So they're terrestrials, but they're intra, meaning not extra, but intra. And
Yeah.
so and these microbes are have a vast expanse underneath the surface of the earth. They connect to each other through these arms that are called arm-like thingies, and uh, and it's envisioned that these global microbes are the biggest form of life on the Earth and known to the solar system. But I think she is also interested in the Europa Clipper mission, and she's involved in it maybe in a peripheral sense to study any kind of microbes that they might get a hint of. And but
Yeah,
that's
I didn't have time to talk about extremophiles on Earth, but I showed a picture of Death Valley. I mean, you find life everywhere. She pointed out way below the surface, but they're bacteria that can live in boiling water. And pHs of like 2. I mean, life is, we find it everywhere. So why not, on Europa?
Yeah.
Yeah.
Yeah,
Thank you.
that's the point, that it's amazing the kind of life that exists all over the earth.
Yeah.
And like you say, it only takes a little bit of water and some chemicals, and then you can eventually get some kind of life. And
Yeah.
so
Thank you.
that argument is used to suspect that life is prevalent throughout the universe, and certainly the solar system. Water is prevalent throughout our solar system. So,
Thank you.
but anyway, I appreciate the talk. It was very good. Thank you.
Thank you. I can't, I don't think I can see the comments section. Oh, here's a question here. Lord Percy Marshall. Yeah. Okay, go ahead.
Hello. Um, I'm just curious. You mentioned that the Europa Clipper had gravity assist from Mars and then from Earth,
Hmm.
but I'm wondering if was there any air braking it used when it arrived at Jupiter, or did it need
No,
to slow down?
no. We don't get anywhere near the atmosphere to do that. It's just going to be it's going to be put into orbit simply with rocket fuel.
Oh, okay. Thank you.
So the insertion into orbit will be done with the rocket. Okay.
Yeah, yeah. There's rockets on there. There are two forms of um, motion capability on the spacecraft. There's rockets, and there's also some reaction wheels to do finer um, maneuvers. But to get into orbit, we're going to use rocket fuel thrusters, or actually the main engine. There's a main engine, and then smaller thrusters. It'll be the main engine that puts us into orbit.
Ah, I see. Okay. Thank you so much.
Mhm. I can't see, since I'm sharing, I can't see the comments in the questions in the chat. So if someone wants to repeat them, if there are any.
Okay, I did so as I said that I posted a few questions, so we can start from that, or we can start actually from Rock's questions. He asked, how much flexibility have you got in adjusting flybys over specific area of interest based on the data from observations during earlier flybys?
Yeah, we have some ability to do that. Um, we do have the ability. The question is, it costs. There's a cost involved in that because you have to have people analyze the motions, the trajectory changes that you have to make. So it's really a cost issue more than a capability. I mean, we could design the whole tour in the middle of the mission, but um, we will we expect to be making tweaks um, to the orbit to look at areas of interest. I think we'll do a lot of that when we're away from the nadir pointing period. Um, we do have, a well-planned mission, but a lot of the mission, especially the far encounter, the period when we're far away from Europa, when we're far away from Jupiter, that part of the mission hasn't really been planned yet beyond just kind of a skeletal structure. So yeah, we will be able to look at plume areas or areas where we may have seen active geology, or things that we can't even envision now.
And the second question that Rock had posted is are you planning to fly through geyser plumes similar to how Cassini flew through plumes on Enceladus?
Yeah,
Enceladus?
yeah, we will. As you said, we did do this on Cassini, on Enceladus, and I forgot to mention that the closest approach distances, range from, 25 to 35 kilometers out to a few thousand kilometers. So yeah, if there are plumes, um, now the plumes might not be if there are plumes, we're not sure really are any because because the Earth-based detections are kind of iffy, and the Galileo detection was iffy too, in my opinion. So because of the gravity, the plumes may not extend as far as those on Enceladus, but we will be able to sniff, as it were, some of the particles in the plumes with the particle detectors.
There's one comment that Rog had posted that reminded to most of us that those that were at IAC when during the launch of Europa Clipper, all the proceedings or basically all the discussions got stopped, and there was a webcast of the launch, and those for 15 minutes that we were just observing, and the 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 whole vibe of this mission is being spread over everyone that attended IAC. So it was quite impressive and memorable moment. And so there's a few questions that I posted. Is what are the biggest scientific unknowns about Europa that this mission aims to resolve? I mean, one is elephant in the room. Obviously, if there's any livable organs, but is there anything else?
Well, I think that we may not even be able to answer that question. We're not a life detection mission. We're looking for we're going to confirm or look for a habitable environment with all the necessary things for life. So we're looking for are there extensive organic molecules on the surface? That's the food part. We're pretty certain there's a heat source. And they're pretty certain there's at least water ice on the surface. But we want to look at the character of the subsurface ocean, its depth, its extent, its composition, and the ice crust, the character of the ice crust, to study the geology on the surface and the composition and whether there's active geology. Those are the main questions.
Okay, thank you. So kind of building up on that question, which instruments on Europa Clipper are critical and helpful for assessing that potential habitability?
Well, the spectrometer, the infrared spectrometer, looks at reflected radiation that has the fingerprints of organic molecules. So that's critical. For the geology, probably the imager is the most important one. For the structure of as I showed on that graph, the slide that showed the similar radar instrument, similar to the Reason instrument on Earth, measuring the character of a subsurface lake. Actually, it's more of a lake, maybe part of an ocean in Antarctica. So for that science goal of understanding the depth of the ocean and the ice crust, the size of the thickness of the ice crust, the radar, and also the gravity science, how the spacecraft tugs, how it's tugged by the moon will show things like the moments of inertia and the interior structure. So I think those are the key, and also the activity is going to be, whether or not there's activity is going to be detected by the camera also, and the magnetometer, because it can show how the magnetic field drapes over plumes. That's kind of how it was discovered. Enceladus plume was discovered on Cassini. And also the other spectrometers, like the UV spectrometer, will be looking for composition as well. And let's see, the thermal infrared mapper, ETHEMIS, will be looking for hotspots, which could also reveal active geology.
Thank you. Kind of a slightly pivoting, but still in line, is Are there any challenges associated with the operations in Jupiter's radiation environment?
Yeah.
So impact from Jupiter, and what is the expected income or outcome impact from that, and then
Yeah.
how your engineering team was dealing.
Yeah, well, the first thing is, as I said, was that our orbit was designed to be away from that environment most of the time. We also have a vault um, uh, with a lot of heavy protection to put our most sensitive electronics
Shielding, yes,
in
radiation
the
shielding.
vault. So those are the two major ways we're going to deal with that. That's the major challenge with the radiation environment.
Okay. And what might Europa surface composition tell us about the chemistry of its oceans?
Well, some of the things we're looking for are evaporate deposits, salts and carbonates, things like that, that would show that there are things that could provide an electrical potential in the ocean. We're also looking for organics, if there's any organic materials that might be exposed on the surface. That's tricky because also photolysis, where you have high energy particles coming in and creating organic molecules out of the more simple molecules that are there. Was it formed by photolysis or did it actually come from the ocean itself? So that's kind of tricky, looking for organic materials on the surface.
Interesting. And if Europa is found to be potentially for habitable, what would be the next logical mission step?
Well, the next mission, and we tried to actually include this on Europa Clipper, is a lander. And hopefully that lander might even be able to rove. So yeah, uh, the lander would be the next one, lander and or a rover. And well, you can't have a helicopter because there's no atmosphere there, but maybe some kind of smaller probes that are jettisoned from the spacecraft, or even little, I don't know if the technology exists for this, but little fuel-powered devices that can go from, jump from area to area. It's all about money. If we had infinite supply of money, we could do all of this. But we're
It's all about
constrained by the
funding.
funding. Yeah, we're constrained by funding.
Those that are involved in space or pretty much in anything, no, there's always constraints. And Rock had asked about what other instruments you wanted to fly but did not make it to the spacecraft, and what instruments would you like to see on a potential surface mission?
I think the most important thing would be a more sophisticated mass spectrometer that could possibly look for isotopic ratios, because that isotopic ratios are very sensitive to the evolution of the moon and also to the possibility of life there. I think that would be the most sensitive mass spectrometer. Not new instruments. We didn't have anything in the microwave arena, but that's because we weren't looking at an atmosphere, and we did have ways of looking at the interior. But I think just more sensitive instruments than new types of instruments.
Okay, thank you. Oh, is there a plan for the mission and then a spacecraft disposal?
Yeah. Thank you for asking that. I forgot to mention it. Yeah, we don't, NASA doesn't like to have missions go on forever, even though they get cheaper as time goes on. Our current disposal scenario is to crash into Ganymede. Ganymede doesn't have the same level of planetary protection that Europa does. NASA doesn't want to put any part of human civilization on a planet or moon that has life potential. So Europa is in that category where you can't dispose of a spacecraft. So we're going to dispose of it on Ganymede. We hope to get an extended mission though.
And the last question that I can see is how close will the Europa Clipper, get to Europa?
Yeah, it's about 25 kilometers, very closest. It's about, yeah, 25 kilometers. That's our closest flyby.
That's very close.
Yeah, it is. On Cassini, we did the same thing too. I think it was about 25 kilometers to Enceladus.
Okay. And any other questions from the audience? You're welcome to raise
I
hand
have,
or just open the mic.
yeah, I have one other comment. On taking off on Lord Percy's comment about the rocket necessary to get into orbit around Jupiter. Um, you might be aware that you can get into an orbit around Jupiter with no rocket at all, but with a close flyby of Ganymede. And
Right. Yeah.
I did my thesis on that back in 1972 at UCLA when I got my master's degree. But you have to fly in an orbit around the sun that has a very low eccentricity
Yeah. So
so that
Mike,
you
what
can,
is the time scale on that? I mean, I knew that existed, but we didn't look into that. How long would it take? I mean,
well, it depends on how long it takes to uh, shape your orbit around the sun to be very
typical.
low
What would the
eccentricity.
typical time scale on that be?
Oh, it would be years.
Yeah, yeah,
I'm
yeah.
not
That's what I
sure.
thought. Yeah,
I don't have the
yeah,
information on the time scale on
yeah,
that. But what I did is I calculated the eccentricity necessary to bring it close to Ganymede and have a Ganymede reduce its energy with respect to Jupiter to below uh, an energy that escapes Jupiter so that you can have an orbit that is around Jupiter. And then that
fascinating.
orbit would be a very long
Yeah,
period orbit at first, but then of course you can fly by Ganymede or other moons of Jupiter to reduce its and reshape the orbit.
yeah, yeah,
And so but it would take much longer time. I think in terms of a few years, maybe.
yeah. That's money. You have to keep that marching army alive. So
That's
that
right.
wouldn't be happen. It's interesting though to know that.
Yeah, but it's a balance between having a rocket do it and
Yeah,
having a much heavier spacecraft going to Jupiter.
yeah.
Uh,
Well, if
so
we have more massive launch systems, I mean, pretty soon we will have, launch systems where we can go in direct trajectories to
yeah,
the outer planets.
right. Thank you.
Thank you.
Okay.
Perhaps just a
Any?
question.
Yeah, go
Yeah.
ahead.
Thanks for the presentation and taking the questions, though. In your opinion, what do you see to be a mission limiting factor at the end then? So, or is it going to be like RCS propellant or radiation damage to electronic solar panels degradation?
Well, we don't know the answer to that because we actually don't know what the radiation damage is going to be. So, yeah, either, it's a trade-off between how much fuel is left and how damaged you are. But again, we don't know the extent of the damage. So I can't, would only be a guess on my part. We have to monitor these. In fact, we do have actually a thing called the canary box on board the spacecraft that is monitoring rate, and we also have a radiation monitor. So it'll be a trade-off between, how much fuel you want to use to do these tweaks to the mission, and how interesting the discoveries are, and how much radiation damage will occur. Both of those things will have to be monitored, and the resources that have to be spent wisely throughout the mission.
Gotcha. And the vault, I presume, is just the titanium box similar to one flown uh,
Yeah.
on Juno.
Yeah, exactly. Yeah. And there's one also on juice, but theirs is more sensitive. Theirs is more of a science instrument. Thank you.
Okay, if no other questions, well, first of all, I want to thank again both our presenter today, Dr. Bonnie Buratti, and all the participants in participating in this program. And also, I wanted to wish everyone happy International Women's Day next week. And as we will be celebrating Women's History Month, I will be sending information on the female leaders in space exploration panel that I am organizing for next Saturday. So with this, thank you very much, everyone. And
Thank you.
thank you for participating and thank you for exploring and being curious. Just keep it up. Thank you.
Thank you. Thanks, everyone. Bye-bye.
Thank you. Have a
Thank
good
you.
weekend.
Thank you so much. See ya. Bye-bye.